Hey there. A while ago, I gave a talk at the Clojure Conch, and in that talk, I showed a few different projects I had made, but I talked a lot about using Clojure as a maker. And I wanted to make this video to show a small little thing I made using Clojure to help with a fun little project um, I had going on. I have an AxiDraw, that's a pen plotter. It's got an XY axis control and an up and down for a pen, and you can use it to make all kinds of cool drawings. A lot of people use it for generative art. I kind of dabble in that space, and I had this idea for a kind of art style that I wanted to play around with. And I had one approach using Clojure to begin with, and then it was slow, not very tangible, kind of hard to work with. So I thought up a little side project, a little tool I could make, and I want to show you that tool and how I use it and how I put it together. So I'm hoping that this video can be kind of just a fun showcase of that, but also a little bit of an encouraging thing to, get your creative juices flowing and see if you can come up with fun little tools to make for yourself as well. They don't have to be Clojure, obviously. The point is more use your computer to do cool stuff. I just wanted to share what I made. All right, so I have this AxiDraw here. It's extremely simple and really awesome. You've got two motors here and a board that you can connect to your computer with USB, and then the power supply there. This is the arm. I can move it by hand freely. You can see the pen is in the up position, is not drawing anything right now. I'm gonna home this, and it's very simple. You just, physically can't go any further, so we call that home. Nice and simple. And here we've got a little servo that will drop the pen and raise it as needed. The cool thing about this is you can use this Axi CLI, and you can just feed it an SVG, and that's what I'm gonna do here. And we're gonna watch it go. The thing I really love about the AxiDraw is it's so simple to get started and get going. I mean, all you need to do is make SVGs. So any program that you can use to make SVGs, you can use to control your AxiDraw. And what's great is, this is a marker, but you can put pens, you can put paint brushes, like you can let your imagination run wild with the materials you actually use here. And yeah, it's great, I love it. So this style that I had in mind, I'm kind of calling a slice render or a contour drawing. It's not exactly contours, properly speaking, but it's sort of a 3D shape with a topological kind of view of things. I don't know, I think it looks really cool. And the fun thing is coming up with shapes that look interesting in this sliced style. And this one I think is pretty cool. It's, well, I'll show you the 3D render of it on the screen in a bit, but it's like parentheses with a sphere in the middle, which is kind of fitting, I think, if you're using Clojure. So there it is. That looks pretty crisp. I gotta say, I'm really happy with that. This is the first time I printed this one, so yeah, pretty happy. Well, there we go. All right, now I want to transition to the computer and talk about what's actually going on here. What did I even build? I haven't shown you that yet. I've just shown you a drawing. So let's get to it. I've got the front end here. I just kind of built this tool up as I went along and figured out how to make things work in a way that made sense to me. So I'll try to explain the details of what's going on and show some of the code that's handling it. I'm not going to go in depth, but I'm going to try to give an overall picture of what's going on. In regular editing, the user will be working on the code here. You're in a Scratch namespace, you've got SDFx.geometry and SVG parametric. You don't need it, but I use it sometimes. You can write whatever Clojure you want in here. When you make a change, the front end detects that and sends off a content changed event, which causes the back end to evaluate the code that's here. Here, a function dispatch content changed, and what that's going to do is create the event content changed on the div here, SDF source. So this is a hidden div. You never see it on the front end, HTMX will listen for the content changed event and will then send a GET request at the /source URL. And the source response is here, and what it will do is run that code and produce WebGL string that's a fragment shader that represents the SDF. It sends it back to the front end. That string gets put back into SDF source here. So you can imagine the content here is your shader code transpiled. Once that's done, on the JavaScript side, a mutation observer that will look for changes in that SDF source container. So anytime the backend sends a shader string into that div and it gets swapped in by HTMX, this JavaScript will detect the change and then run the function redraw. And what redraw is doing is compiling that fragment shader and running it in the animation loop. In effect, what you get is anytime you make a change, the backend evaluates it, sends the string shader code, and then the front end incorporates that back into the shader and it keeps the animation loop going. That's why you can pan and move the camera around here and then do this. It just reruns that shader code, and everything else, all the other values are staying the same. You press the button get contours and then it runs the function grab pixels, and that's a front-end piece of code. By the way, I'm not a JavaScript expert. I had the ideas of how I wanted to approach this, and I actually used ChatGPT to help fill in some of the knowledge gaps. I guess here be dragons. It's not perfect code, but it is code that does what I want it to do. Perfect for a little tool like this. Grab pixels will group all of the pixels by their color, which is why I have the shader actually returning for each Z layer a color that's shifted in hue, basically, so that it's a little easier to kind of group those pixels and get a contour at those given slices. Grab pixels is running that code that gets the contours, groups those pixels, then it does an edge trace to get just the outer pixels, and then I just take the coordinates of those pixels as if they were polygon points. Then I send that map as JSON to the backend to the /contours path. And then what I do is run this contours response. Details, again, are not that important for sake of demonstration. What it's doing is taking that map and turning it into SVG, then sending that SVG back to the front end, and that will get rendered into the contours container here. That's what's going on. You've got front end sends the source to the back end evaluates it, sends the shader code to the front end evaluates that. That's your editing. Then when you're happy, the front end gathers pixel data, sends that pixel data to the back end calculates the SVG, sends the SVG to the front end, renders as SVG here. And then there's a few miscellaneous items. Docs, which just sends a get to the /docs URL. That just runs, it looks at the metadata in the namespace publics and just formats it nicely. Gallery looks at a history atom on the back end and pulls that data and the source code that was available to produce that, formats it nicely, sends the HTML over, HTMX swaps it in. Finally, the save button sends the file name that you want to save it as to a save post, and then the backend will look at the last history item and try to save that SVG data out to output / the given file name. That's all the mechanisms I have in place to actually get this to happen. The next thing I want to show is a very quick demonstration of how I actually make the shader code on the backend. I've set up a SDF demo namespace, and I'm just going to quickly go through what I've got here to kind of give a light overview of what SDFs are, but also show you how I started understanding SDFs using Clojure and Clojure's higher order functions. So SDF is a signed distance field. They're useful as ways to define geometry. Distance refers to the minimum distance between some given point and the surface of the shape that you're looking at. The sign indicates if the given point is inside, negative, or outside, positive, the shape's surface. So I can't totally explain fields in the mathematical sense. Luckily, we don't really need to know about it to be able to use them effectively. For the SDFs, we have a few primitives, a box, a sphere, and then we have some actions that we can do on them. Translate, union. Those concepts alone let you build up more complicated shapes, some of which you've seen in my earlier demo. Let's get to it. Let's start by defining a distance function. Let's just do distance 0, 0, 0 and 10, 0, 0 as a sanity check, and 10, 10, 10. Okay, and so let's create our first SDF. We have here sphere SDF. Let's define that. Try it out. It takes a point. Let's just do 0, 0, 0. So the origin. Let's see what this returns. It gives us a value, a distance of -1. So the negative means that the point 0, 0, 0 is inside the surface of our sphere SDF. We've got 1, 0, 0. That's 0, which means that this point 1, 0, 0 is exactly on the surface. It's a sphere, right? So we would assume that -1 in the y direction would also give us 0, and that's what we see. Now -3, I just wanted to use as an example to point out that the distance returned is not dependent on any of the signs of the coordinates that you're using here, right? It's 3D space. The distance, in this case, to the surface of the sphere is 2, which kind of makes sense. If you picture a sphere of radius 1 on the origin and you pick a point 3 units away, the distance between the surface is going to be 2. Here, right, it kind of becomes unintuitive quickly. I can't picture this easily in my head. What distance it's going to be, 0.7, 0.7, 0.7. Okay, that's nice to know. This number here, it's actually very close and on the inside, and I wouldn't be able to tell you that off the top of my head. That's just the unit sphere. What if we wanted to change the radius? Here is where Clojure's higher order functions kind of come in pretty handy. I can turn the radius into a parameter here and emit a function. So now I've got a sphere creating function. I can do sphere 20, and if you look here, it returns a function. In the REPL, I can take the last input, star1, and I can run it, and I get a distance of -20. So I can def a in the REPL here as sphere 20 if I wanted to, and then I can run a because it's a function and get a distance. These higher order functions are a way to more tangibly actually create geometry. Like this sphere of radius 20 is that function, and I can give it a point and get a distance back right away. I can just ask it. Let's explore this just a little bit further. So what if we wanted to move our sphere away from the origin? Now we can look at just the general form of this. I can make any arbitrary function I want with any number of parameters, and as long as it returns a function that expects a 3D point and returns some number, distance, then I can use that in my SDFs. It would be more useful to create a translate transform that can work on more than just a sphere. So that's why I don't reach for, putting it in as a parameter here. How would I do that? Okay, here's the translate function. It takes in a shape. It's a function that expects a point and returns a distance. What it actually does is before running that function shape with the given point, it just moves the point. Here's how it looks to use. Let's make a sphere 20 and translate it 20 in X. So what this means is I've got a sphere no longer centered at the origin. The center of the sphere is 20 units in the positive X direction. So when I run that shape, I should expect that that point is exactly in the middle of that sphere. So let's see. Indeed, we get a distance of -20, which is the middle of the sphere. All I'm doing is moving spheres around now. That's fun, but that's not particularly useful. I'm going to show you one final thing, and then I'm going to get into the next phase of me showing this project. The box function will return a function that expects a point, and it will return a distance. You can kind of work through this yourself if you want to, or just trust that it works because it happens to work. I've got this box. It's 10 by 10 by 10, centered at the origin. The position 5, 5, 6 is, at the corner of the box, +1 in the Z direction. The distance is 1. Pretty sensible. So now that I've got two shapes to work with, a sphere and a box, and a translate, I can move them around. I want to also be able to combine them. And the cool thing about a distance field is that the output of your distance function is just a distance. What we can do is combine any two different SDFs with a minimum distance. It'll be this one. That's your answer. So you just use min and you run shape A and shape B. You check the distance to those points, and then you get the minimum. This now is the end of my very brief SDF exploration. I just want to point out this one thing though. Let's take this shape, which is the union of a box and a sphere. I want to run that shape's position. 0. The only way that that would make sense to you is if you sit and redraw this shape in your head and think about the geometry, which can be a fun exercise, but it starts to grow pretty tedious especially when you're randomizing things and you don't know where your shapes might be or exactly what size they are. What you really want is a visual for something like this. I don't want to have to draw the full 3D scene in my head every time. Even if I could do that, why? Why would I do that? It's a little slow. So this is really the essence of the motivation I had for making this tool to begin with. I wanted to quickly play around with SDFs and see what they look like. I wanted tangibility of the shape, right? Okay, I have to come clean. I was kind of lying about how my SDFs work earlier. I showed you the higher order function approach I use to make spheres and boxes and stuff like that. And all of that's true. I actually have different libraries that do exactly that. But what I found is while I was working on coming up with a way to render the SDF in WebGL and simultaneously have the functions useful in the backend, I realized it kind of makes sense if I just make my backend emit shader code required from the start. So what do I even mean? Let me show you SDFx.geom's version of the sphere function. Right, so in this sphere function, right, I just added this for demonstration purposes. In fact, I should take this conned out entirely. This is a holdover from when I was first starting on this. The original idea was to perform different behavior based on the input point. What I should really focus on, though, is this string version here, because I'm actually not interested in sending a point into the sphere function. What I want to do is actually just put in the string p, and what it'll output is this here, sdsphere p.2. So what's happening? First of all, I want to quickly point out that I've got this let r be r times the internal scale. This is a little dynamic var that I put in there because I wanted to control the assumed scale of the numbers in the editor and make sure with the SDF rendering that the scale wasn't too out of whack. That's why instead of 20, you're seeing 0.2 because the internal scale is 0.01. The important thing is I'm emitting this string SDSphere. Now this function SDSphere is not defined anywhere on the back end. It's actually defined in this render code. What I've done is I've got the first half of the frag code has some primitives built in right here. I've got SDBox, SDSphere, and what this is doing is actually creating, like this is where the SDF functions are defined. On the back end, I'm just using those functions to build up a string that is the SDF, plunk it back into the fragment shader and run it. All the stuff it needs is there, and it produces the image you want. You know, if you look critically at this, you could see that maybe this is not the most expandable approach, right? Because if I want to define some new primitive, I have to make sure I'm either defining it using existing primitives, so it's not actually a primitive, it's a composite, then I can just do it on the back end. But if I want to truly make a new primitive, I have to add it in the shader code and then add a function to emit it in the back end. But this is a small tool doing what I want. This is what I came up with and it works. So I'm pretty happy with that. Let me quickly show you what, a translate will look like. Let's do sphere 20, translate, and of course I have to actually run the function like this. You've still got SDSphere, and the translate operation is not changing the SDF function itself. It's changing the point that you're sending into the function. So if you have a look here, it's the SDSphere. It's still just looking for a point, and it still has a radius right here. The difference is I've kind of like spliced in this translate function that takes the original point and then runs translate with the input vector here. So that's the basics, but I'm gonna quickly copy paste this into the REPL and evaluate it there with a string, so you can see like what it's actually outputting. It's not pretty, but it does work. Right, okay. There we go. You know, that starts to look a bit ridiculous, right? Like, got a union, intersection, smooth difference, box, translate. Like, you could, you know, write this all yourself, and if you were to write it yourself, it would certainly be structured differently. But I just think it's really quite handy to be able to define these shapes and just not worry about the shape of the output shader code, right? Like these just work. And I can go into each of these functions and define, you know, like I was showing earlier, the higher order function versions of these, and get the exact equivalent SDF that is actually a runnable function on the Clojure side of things. I just think that's really cool. I think it's a fun way to approach this. Is it definitively the best? No, for sure not. But it's exactly what I came up with, and it works to do what I want. I mean, I showed you at the beginning of the video an actual output onto paper using the AxiDraw, and I'm just super happy with that. And I just want to show a little recording of me just kind of hacking away on this now. Okay, I've got basically a blank slate here. I'm going to switch this to normal color here, and for now we're going to ignore that. And I just want to kind of work through this, talk out loud. I'm going to try, because I just deleted the code, I'm just going to try recreate the parens piece that I came up with earlier. I mean, worst case scenario, if I don't have it exact, I've got the code in the gallery, so I'm safe, no worries. Let's tackle this, let's go. Right, so we've got a sphere here. By the way, if I hold Control and press up or down on a number, I can it'll change the value. If I hold Control Shift, it'll change it by 10. Fun little, like, super useful hack. Let's start by taking this sphere. You know what? Let's just bump it up to 90. It's not working because the code's broken at the moment. Let's do G onion, and we'll do 10. Okay, so what's onion? Oh boy, let's zoom that out. It's not going to look like anything now, but it kind of turns your solid shape into a shell. This value is approximately the thickness. Define that to be A. I'm using lazy names. Let's do difference A and a box of size 100. Oh, you know what? I forget that the box is like that. Okay, so there's a box. The difference between A and the box is not making A very visible. Okay, see here, this is actually a pretty good example. This is not the difference I wanted to show, but you can see that the difference, if I take away A, which is that onion sphere, from this box, then this is what I get. Take that away, there's no interior to it anymore. That means the sphere is solid. So that's what onion's doing. But let's swap these around. Do difference and then A. Okay, now you get a better, that's a much easier thing to visualize. So let's go with that. So there's the slice, the onion, oops. You get pretty cool, weird artifacts if you do zero width things sometimes. It's kind of fun, but it's not what I'm after today. So let's pop that up. And you know what? I actually want to do this. Let's make this 40 and this 110, and we'll do it kind of oriented this way. It doesn't make a big difference, but I think that's how I had it at the start. That looks about right. I think that's pretty good. We've got an onion sphere kind of chopped in the middle a little bit. Let's call it B, intersection between B and another box. Oh yes, I need to do G intersection. Might have frozen it as it turns out. Interesting. Well, let's refresh it, see what's up. Okay, so this is, you know, not a perfect tool, but let's try to keep working with things anyway, right? There we go, that's what I'm looking for. Okay. Right, so now, you know, despite that little hiccup, we've got, these are looking like parens, right? So one thing I actually had going for this earlier is not just a difference, but a smooth difference, which actually takes another parameter here and, like, as you can see, kind of smooths things off, which I'm pretty happy with that. Like, that looks nice, right? But to make it sort of match, let's do smooth intersection 10, do the same kind of thing. I think that's nice. Let's define that to be C. Another little problem I've got with this tool is it doesn't format, like the editor is not smart like Emacs is, right? It's not structural editing, it's just paren matching and indenting. Another little thing that I could fix but don't really need to have it working. The last thing I want to do is actually take g/intersection of C and a translated box. Let's this time make it 50 by 50 by 130. Translate that. Oh no, let's translate it 50, 0, 0. Okay, so we've got something kind of weird happening here. Maybe I mean difference, and I mean to do this first, like that. Okay, right, so what I'm actually doing here is trying to cut away one of the parens because I only want one so that I can pair them up manually and change the distance. So I just need to get rid of one. Okay. Okay, so I think I've kind of oriented myself all backwards here, but okay, there we go. Combine this into another step here. So you can see as well, as I'm going, I just let things get a little messy. If you like a design, you can kind of optimize how you've written the code later. Okay, so now let's do union. So let's say we've got D is, let's do paren instead of D. So let's do union paren and a G sphere 50. Here we go. We're getting close to the end here, right? Let's bring this so that it's like, let's do like that. Yeah, I think that makes some sense. What I'm trying to do is sort of align the paren's vertical axis kind of at 0, 0, so that if I rotate it around 180, it looks a little bit correct. So if I copy this one, and I know I want another parenthesis somewhere else, I want to translate it. Paren G translate, let's do 0, 0, 0, 0, 0, 0, like this. Second one here, I also actually want to rotate it, 0 on X, 0 on Y, and 180 on Z. And actually, I realized here's a mistake I made. I need to actually do reduce union and then send it a list of things to union together, because union only takes two shapes and then combines them. There's also a singularity call to union, which just returns the shape, which makes it possible to do reduce. It'll just do pairs and pairs and pairs until you're done. You've reduced it to a single shape, which is just the union of all of them. If I take the definition of the parenthesis and I move this, you can see them changing here, right? And that's because the rotation happens around the origin. So if your base shape is way off in the origin, you'll kind of sweep it a long distance like that. It's nice to have a sort of sensible origin for the paren itself, which is why I had it kind of like that, 60. That does mean, for this simple drawing, I do have to shift this back by the amount that I adjusted it, but it's a nice way to think of these things sometimes, to give yourself a little more flexibility when you're defining the shapes themselves. That's good enough for now. Say I want a bigger sphere here. Final little step, if I do the get contours now, I'm going to get a weird result, and that's because I haven't sliced and turned the Z contours on. I have a function in here that I can use. It's g/slices, and it has a spacing and a thickness value, and that should handle things. So there we go, we've got the slices. Now let's turn on the Z contour. There we go. We're building up basically a similar shape to what we had before. Let's get those contours. Okay, let's fiddle around with the values here. Let's just shunt it up by like 0.2. I don't know, maybe that'll help with these artifacts. This is the nature of working with a sort of tool. The goal is not to necessarily get a perfect product, it's to get something I can use to post-process and send to the machine. Because I'm still the artist here, I still have to make decisions and take actions, right? I can't just, well, I could, I just don't want to hand it entirely over to the machine. I want to do some of the work myself. Let's get a true zero distance there. Let's see if that's kind of close to something cool. There we go. Okay. Open up the gallery one more time and just have a look at, let's say, one of the ones that was working before. I'm pretty happy with this one. See, this is my version of like saving the history. You could just copy and paste the bits and pieces that you made before. Simple and effective, gotta be honest. I like it. There we go. Let's get those contours. There we go. Okay, that's how I used the tool. That was a kind of helter-skelter tour of what I actually did, how I achieved it, a little bit of the technical details, but not everything. I hope you enjoyed watching this video. I had a really fun time making this, and I'm gonna keep having fun using it as an art tool. I'm gonna keep exploring. I'm sure I'm gonna expand some of the functionality of this as I make more pieces. You can have a look at that. You can post issues if you want. You can critique and kindly criticize the code, make suggestions for improvements if you want, by clicking the link in the description to the GitHub that has this project. You can actually also download the jar from the GitHub and run this yourself and play around with it. I think that would be pretty cool. That's all I've got to say about this. I hope you enjoyed having a look at this tool that I made. I hope it made some sense, or at the very least is kind of cool to see in some way. I hope this inspires you to try making tools for yourself and to not worry too much about things being perfect. Just come up with the thing you want and do it, you know? It truly doesn't have to be amazing. It can be a really simple tool. It can be a complicated tool with a simple set of approaches that you cobble together with ChatGPT or other people's advice. It really doesn't matter. Like, computers are awesome tools, and it's really awesome when you feel comfortable just trying to build stuff. That's what I want. I want you to build stuff. I hope this is inspiring, and I hope this was cool. Thanks very much, and have a good one.